Okay, we're on 2-1. So we are starting chapter 2, and if chapter 1 was more challenging for you, I've had students who do better in chapter 2 than in chapter 1. So don't let that deter you or worry you at all. So this unit is all on reasoning and logic and proofs. And so we're starting with a special kind of reasoning called inductive reasoning. And it's the process of using observed patterns to make conjectures. Remember, a conjecture is an educated guess. It's like a hypothesis, it is in science, but we use the word conjecture in math. So we're making just educated guesses, just a statement that we don't know is true or false. We're just making it based off of an observed pattern. So I want you to know that everything in an inductive reasoning is based on patterns. It's based on observations. So we're observing and we're looking for patterns here. We have a couple examples that we're going to look at first. We have one that's a picture. So it says sketch the next figure in the pattern. So from the picture I see I've got a circle with 2 lines and then a dot that's in what looks like the top left quadrant. Then I have the same picture, a circle with 2 lines, but this time the dot's in the top right quadrant. The third one's a circle with 2 lines and the dot's in the bottom right quadrant. And now I'm going to have a circle with 2 lines. I think we all know that. Where's my dot going to be?
The bottom left.
The bottom left. Very good. Bottom left. So it just says sketch the next figure. I don't need to draw more than one. I just have one. So put it in the bottom left. Awesome. Move along. Next, I have sequences of numbers. So we're going to find the pattern with those numbers. I like to start by looking for adding and subtracting. If that doesn't work, then I multiply and divide. And if that doesn't work, it's kind of a funny case and we'll have to see what that pattern is. And that's more of a special one-on-one kind of thing. So this first one, I go from 5 to 3, from 3 to 1, and then 1 to -1. I can look and I can see pretty easily. I just -2 to get from 5 to 3. I do have to make sure that works for all of the numbers though. So I'm going to do, okay, does 3 minus 2 equal 1? Yes. Does 1 minus 2 equal -1? Also yes. So my pattern, I'm going to describe my pattern as subtract by 2 or -2 or something, add -2, whatever you want to say. That's what you do each time to get the next number. In addition to describing the pattern, it says find the next number. Well, the next number is going to be whatever -1 minus 2 is, which is -3. So I described my pattern and I wrote the next number. Awesome. Any questions so far? All right, next one. I'm going to look and see, can I add or subtract here? Okay, well, to get from 1 to -4, that's -5. But -5 minus 4 doesn't give you -9. Wait, sorry. It does give you -9. It doesn't give you +9, which is what I want. So that doesn't work. Okay, it's not -5. What if I multiplied or divided? Okay, 1 times -4 would be -4. Okay, but does -4 times -4 give me +9? No. Okay, so this is one of the weird ones. If I look at these numbers, I have 1, I have 4, I have 9, and I have 16. Those are all special because they're perfect squares. 1 is 1 squared. 4 is 2 squared. 9 is 3 squared, and 16 is 4 squared. The only other thing that I have going on is every other one of them is negative. So when I describe this pattern, I'm going to say perfect squares with alternating signs. So essentially they're alternating between positive and negative and positive again. Ooh, come back. But it's a list of perfect squares, but the signs on every other one of them is different. So positive then negative, then positive then negative. So I predict the next one is going to be positive and it's going to be 5 squared. So 5 squared is 25, positive 25 is my next prediction. Any questions so far? All right, the last one's just a fraction one. It's not difficult math, but sometimes what gets confusing is that with fractions, we just kind of panic to begin with. So let's look at this carefully. This is going to be a multiplication or division one. Oftentimes fractions are. In order to get from 1/2 to 1/4, my first thought was multiply by 1/2. And I'm going to do the math off. I'm going to erase this in a second. So if you just want to watch, that's cool. If you want to write it down, also cool. 1/2 times 1/2. Remember with fractions, we multiply the top and we multiply the bottom. So 1 times 1 is 1, 2 times 2 is 4. Okay, that works. Now does 1/4 times 1/2 give you 1/8? Again, multiply the tops. 1 times 1 is 1, 2 times 4 is 8. So yes, that does work. So one pattern is multiply by 1/2. And I'm going to write that down. Now, sometimes your brain doesn't work like the multiplying. Sometimes you want to divide. Sometimes you want to divide, and if we did 1/2 divided by 2, well, my question is, does that work? When you do divided by 2 to a fraction, that's the same thing as multiplying by the reciprocal. So that's the same thing as 1/2 times 1/2, which I just showed you works. So I'm going to write divide by 2 because that also makes sense. That is also an okay pattern to find. Okay, any questions? Oh, sorry, I gotta do the next number. So if it was 1/8 and then I multiply it by 1/2 or divide by 2, then it becomes 1/16. All right. The next part says inductive reasoning process. So this is just kind of what you're doing. 1 through 3 is like your mental process. I'm not gonna make you list this. So first thing you do is you look for a pattern. Then we make a conjecture. Remember, that is an educated guess. It's also unproven and it's based on observation. And then we have to decide whether it's true in all cases. So we're going to do 2 examples where we're making conjectures. If I say make a conjecture, I mean like write a sentence or use like your math signs to say like something equals something. Like you should have a sort of sentence about this. So the first example is asking us to make a conjecture about the sum of 2 odd numbers. So sum of 2 odd numbers, I've got 1 plus 3 equals 4. I'm just doing some examples. Okay, 1 plus 3 is 4, cool. 1 plus 5 is 6. Okay, seems fine. 3 plus 5 is 8, and 9 plus 7 is 16. We don't need to do every single odd number added in the whole world. We just need to do enough to make an educated guess. My educated guess now is looking at a pattern. I see 4, 6, 8, and 16. They're all what kind of numbers? Those are all what kind of numbers?
They're even.
They're even, good. Heard a lot of voices on that, which means that we all knew that. They're even numbers, okay? So because of the 4 examples that I saw, I'm going to assume, I'm going to make a conjecture that the sum of any 2 odd numbers in the whole world is going to be an even number. This sentence right here is my conjecture. That is like my answer to this problem. And since I wrote that, I'm done and I'm ready to move to the next one. Okay? The next one is more of a geometry one. It says, okay, we want to make a conjecture about the relationship between A, B, and E, F. So at the end, I'm going to write something about A, B, and how it's related to E, F. And that's based on this info right here. AB is equal to CD, and CD is equal to EF. Now, you may already think you know what it is by just reading it, which is awesome. But in case I had no idea, I'm going to draw a picture. Because remember, when in doubt, we draw pictures. I'm going to label this. I'm just making a big, long segment with all of these points. A, B, C, D, E, F. It says AB is equal to CD. Okay, their distance are the same, their lengths are the same, their measurement is the same. Then it tells me that CD's measurement, distance, length is also the same as EF. What conjecture then can I make about AB in reference to EF?
They're equal.
They're equal to each other. They're equal to each other. I can say AB is equal to EF. Or I could say that the segments AB is congruent to the segment EF. Either one of those is okay. Now, if you don't like writing expressions like this, you can write a statement. I can say they are equal, or they have the same measure or length. Whoa, that's not a high school measure. Pretend that's an R. Or length, or distance, or we could even say they are congruent. This is essentially like 5 different things that I could write, and these are all conjectures. So you don't need to write every single one of these, but I'm saying there's a lot of right answers we could come from this. I mean, we could also write a false answer. We could say something about something else. I could say AB is less than EF. It may not be true, but I could say it because a conjecture is just an educated guess. It does not have to be true or false. Okay, turn to the next page. We're going to make some conjectures based on this picture. So there's a lot that we see right here. So based on what we see, we're going to write a conjecture. We're going to write a statement. So what's something that you see here that we can assume or that we're going to guess about this picture?
One is a 90-degree angle because it has the square, and so I'm going to assume that all the other ones are 90 degrees.
Okay, I'm going to stop you right there. I'm going to say angle 1 is a right angle because it's labeled. Good. Jade, what did you say?
They're all congruent.
They're all congruent. All the angles are congruent. And then Ava, based on what you said, this goes with what Jade said, what are all the angles measurements?
90 degrees.
They're all 90. So all 4 angles are congruent, and they are all 90 degrees, or they are all right angles. Awesome. We see this little mark right here, and we wrote 3 sentences very, very quickly about what we can see based on this picture. I want us to dive a little deeper too. There are some relationships between these angles. What's a relationship that you see or that you can tell me?
1 is vertical to 3.
Okay, 1 and 3 are vertical. Are there any other vertical angles?
2 and I can't see. 2 and 4.
2 and 4, okay. 2 and 4, good. All right, so vertical angles, we see that those are there. They're also congruent, so I could have said 1 and 3 are congruent. I could have just focused on those 2. All right, somebody new. What's another relationship I have here?
1 and 2 are adjacent.
1 and 2 are adjacent. Very good. 1 and 2 are next to each other. They share that vertex and that side. I want to focus in on 1 and 2. In addition to being adjacent, there's a couple other things that are cool about them or that they are related in. What else do I know
They're
about
supplementary.
them? They're supplementary. Very good. And if they are adjacent and they are supplementary, what's another word I can use for them?
Linear pair.
Linear pair. Awesome. Those are all true things that I can write about this, and you could have just written one of those things, and that is one conjecture. So we're writing a bunch of conjectures about this picture. We could have also said the same thing for 1 and 4, or for 4 and 3, or 3 and 2. There's a lot of options on what we see here. Before we move on, though, I want to think about the lines. So we've been focusing on the angles. What if I named the lines L and M? What do we know about the lines?
They intersect.
They intersect. Just basically, they intersect. And do they intersect in a special way?
They're perpendicular.
They're perpendicular. And how do you know that?
Because 1 is measured and it is a right angle.
Good. Remember on that worksheet I gave you the other day, it had this little sign right here, this upside down capital T. That means perpendicular. So I'm just going to write it on our notes, and I'm going to write perpendicular next to it just so I can have it to reference back to later, later if needed. And then the other thing that isn't said, and that took me a while to think about, but it is true, is L and M are coplanar. There is no other planes drawn on here, and so I can make the conjecture that they should be on the same plane. All right, so we just made a ton of conjectures. If I ask for one, I just want one of those things to be true. All right, any questions so far? Okay, the last concept we're going to talk about today is something called a counterexample. A counterexample is an example that shows that my conjecture is false. So it's one example that shows that the statement I made is not true. Now, it only takes one counterexample to prove that a conjecture is false, which means that it's so much easier to show that it's false than it is to show that it's true. In order to show that a conjecture is true, it means that it has to be true all of the time. So I have to show every situation means that it's true. A counterexample leads me easily to say, oh, no, that's not true. So a real life example we could think of for counterexample is I could say, all geometry students are sophomores. Well, that's not true, right? I think we have a freshman and a sophomore and a junior in our class. It just depends on your math career. Some schools do Algebra 1, Algebra 2, then geometry. Some schools do some of that in middle school. So then you're in geometry as a freshman. Sometimes you do Algebra 1, then geometry, then Algebra 2, like whatever. Just because you are a geometry student doesn't make you a sophomore. So by naming a freshman or by naming a junior, that would give us a counterexample. If I had said it the other way, if I said sophomores take geometry, a counterexample of that would be a name of somebody who's a sophomore who doesn't take geometry. So those are real world examples of a counterexample. Now we're going to do a couple math examples. So this first one says all odd numbers are prime. That is a conjecture. And I'm going to say that it is false. And we need to find a counterexample that proves that that's false. But first, what does prime mean?
It means that it can only be divided by itself and 1.
So like 2 works as prime because the only things that multiply to be 2 are 1 and 2. Like 5 works as prime because only 5 times 1 gives me that. Like, I don't know, 23 or 29, I guess. Those are prime because they don't have any other multiples. So those are all examples of prime. Now I need an odd number that is not prime to be a counterexample.
9.
9 works. 9's 3 times 3. That's not prime. Anyone have another example?
15.
15 works. That's 5 times 3. Any other examples?
21.
21, very good. 3 times 7. We could do this all day, right? There's a ton of examples we could come up with. Every single one that you guys listed, though, that is a great counterexample. Once I listed any one of those, I'm done. I don't need to list every single odd number that's not prime. I just need to show one is not prime, and then that makes it a counterexample. That makes this false. All of these are odd numbers that are not prime. I'm going to say, but not prime. And so any odd number that you picked that's not prime, that works as a counterexample. Okay? The next question is really wordy, but stick with me. It says the square of the sum of 2 numbers is equal to the sum of the squares of 2 numbers. Yuck. Okay, I have it written here mathematically, but let's dissect it really quick because I believe that you could have written that by yourself. It says the square of the sum of 2 numbers. So the square is right here, and it's the sum of those 2 numbers is equal to the sum of the squares. So I'm going to do this. I'm adding the squares. So it just depends on how I put my square and where my parentheses are. Now, this is not like the last one where I can just like know a number. Like I don't just like know a number off the top of my head that makes that false. But I'm going to argue that you can plug any number in here and that will make it false. So I can make A like, I don't know, 3. And I can make B like, I don't know, 5. Sure. You can pick any number. You could have picked 4 and 2. You could have picked 1,300,000,000. Like, I don't care what you pick. I'm just going to try and keep it really simple and basic for myself. So I'm going to plug in 3 for A and 5 for B and kind of see what happens. So I'm going to do 3 plus 5 squared equals 3 squared plus 5 squared. Now, I took a bunch of proof classes in college, and every time we had an equal sign that we didn't know was true, we put a question mark over it to say, okay, this is what I'm checking, but like, I don't know if it's true or not. So that's what I am used to writing. You don't necessarily have to write that. I think it's cool though. So let's start simplifying. 3 plus 5 is going to be 8 squared. 3 squared is 9. 5 squared is 25. Again, I still don't know if these are equal to each other or not, so I still have my question mark. 8 squared is going to be 64, and then 9 plus 25 is 34. Are those guys equal to each other?
No.
No, not at all. Not ever. Not even a little bit. No, 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 no. So because those did not equal each other, 3 and 5 are my counterexample. My counterexample is, okay, here's one time it didn't work when I plugged 3 in for A and 5 in for B. You could have plugged any number in and I promise it wouldn't have worked. Okay, that being said, if A plus B squared isn't the same thing as A squared plus B squared, do you remember how I expand this out? How do I algebraically multiply this?
You FOIL it out.
You FOIL it out. I need to write it a little differently though. Maggie, can you set it up so I can know exactly how to FOIL it out? Since I have this square, I can rewrite this as what times what?
Oh, A plus B and then A plus B.
Good, that's what I was leading you towards. Sorry, that was a terrible leading question before that. But yes, you're right, we have to FOIL it out. So I want to write it like this, A plus B times A plus B in order to know to FOIL it out. What's gonna happen is I'm gonna get a middle term that we didn't have before. So A times A is A squared, A times B is AB, B times A, when you multiply, remember it's commutative. So I can write BA or I can write AB, and I wanna write AB so these guys match. And then last, I'm gonna have B squared. I now get to add those two together. So I've got A squared plus 2AB plus B squared. And do you see how that is different from this up there? That's why that would never work. Mathematically expanded, this is that expression, not what we had up there. So that's why that's always false. And this is a common mistake we make. Even my seniors make this mistake sometimes. So I wanted to point it out to you guys so we don't have to make it. Okay, any questions on your notes? Anything so far? Okay, I do want to jump over to our homework really quick. So I'm going to jump over to homework. So it's either under homework 2-1 or it's attached to homework number 12, whichever one you want to pull. And I just want to go over a couple things. So 1 through 6 is like that box that we did right at the beginning of your notes, where we either drew a picture or we had numbers and we had to find the pattern and then write the next number. So 1 through 6 should be pretty easy. You guys should be awesome at that. 7 through 10 say make a conjecture. In order to make a conjecture, I need to write a sentence. So your sentence should be like, this is a right angle. These angles are linear. This is a vertex. Like you should have an actual sentence for these. If you come in on Wednesday with this blank and being like, oh, I don't know how to do it. No, that is unacceptable. You guys are smart, write a conjecture. It doesn't even have to be true, but all of these should be sentences, okay? On the back side, the directions say, determine whether each conjecture is true or false. Every one of these should say true or false. Then it says, give a counterexample for the false conjecture. So every time you write false, you either need to write a sentence or draw me a picture that shows a counterexample that shows that that is false, okay? So on the back, everything should say true or false, and then some of them should have pictures or like another sentence for you to tell me why that's false. Okay? Any questions? Okay, I'm gonna stop sharing and I'm gonna